So these PowerPoints on the periodic table pretty much cover all of Chapter 7 in your textbook. So make sure you read those pages as well as watch the video and take some notes. All right, so kind of going through the periodic geography stuff, just reminding you where metals, metalloids, and nonmetals are located. Remember that even though hydrogen is over in the metal area, it's really a nonmetal, but it only has one electron in its valence shell, so that's why it winds up going there. Remember that metals typically give up their electrons in order to become stable, while nonmetals try and gain electrons in order to become stable, which is another reason why hydrogen's there. Even though it's not a metal, it'll lose its electron more easily than it does want to gain one. Metalloids, kind of in between properties. Notice they're right along that stair step, except for aluminum. Aluminum is definitely a metal. All right, so if you remember some of the properties, metal characteristic increases as you go down, so the metals down in the bottom left-hand corner show the most metallic properties. It decreases as you go across, so something like aluminum, it shows less metallic property than something like potassium does. You can read the rest of these ideas. They're shiny and gray. They're ductile and malleable. Ductile means you can draw them into wires. Malleable means you can pound them into sheets. They're good conductors of heat and electricity. Metal oxides, so LiO or Li2O or MgO or something like that, are typically ionic solids and create basic solutions when you dissolve them in water. Like we said, they lose electrons to form cations. And as you will see, or maybe you remember, low ionization energy, low electron affinity, that's something new, and low electronegativity. Nonmetals are pretty much the opposite. Nonmetal character increases as you go across. So francium is going to have the most metal character, but fluorine is going to have the most nonmetal character. So you put the two of them together and you would wind up with a very violent reaction because francium wants to lose that electron and fluorine wants to gain it very, very desperately and very, very easily. You can read the rest of that stuff, pretty much the opposite of the properties of metals. One note, nonmetal oxides are molecular and they create acidic solutions. So metal oxides create basic solutions. Nonmetal oxides like nitrogen dioxide, nitrogen trioxide, sulfur dioxide, those things make acidic solutions. And so here are some of those reactions that we just mentioned. Metals are going to react with acids to give you a gas. Isn't always going to be hydrogen gas, but often will be hydrogen gas. Like we said, metal oxides will react with water to give you a base. And then metal oxides will neutralize acids. So because they create a base in water, the OH minuses will react with the H pluses and give us H2O neutral stuff. And then nonmetal reactions, again, we said nonmetal oxides react with water to form acids. This is actually how acid rain is formed. This is one of the culprits of acid rain, NO2. SO2 and SO3 are the two other metal oxides that are associated with acid rain. They form sulfuric and sulfurous acid. And then nonmetal oxides will react with bases in order to neutralize it. So because these guys react with water to make an acid, they will neutralize the base. All right, so moving on to some more geography. We've got the different families. So remember the alkali metals, sodium, potassium, and so forth are +1s. Alkaline earth metals, calcium and magnesium's +2. We got the transition metals in the center. Boron, carbon, boron goes +3, carbon will go +4 or -4. Mostly it just forms covalent bonds. Nitrogen family will go -3. Oxygen family, also called chalcogens, will go -2. Halogens go -1, and the noble gases tend to not react. And then you got the lanthanide and the actinides. That's because those are the elements at the head of the line. So we talked about charges before, but here is kind of an overall idea of the charges. Note that boron, carbon, silicon typically don't go plus either. But if they're going to, boron will do +3. Carbon and silicon can go either way, but again, they would much rather share electrons than gain or lose electrons. Here's the pattern. The transition metal stuff you don't really have to worry too much about. But notice the metals over in the P block will go +2 and +4. So now why is that? They'll lose these 2 electrons to go +2. Then they'll lose these 2 electrons to go +4. Actually, these go first. These are going to be gone for +2, and these will be gone for +4. Antimony, same idea, +3 and +5. In between, you've got various charges. We're not going to worry too much about what they are. There's no place in the AP exam where you actually have to know a charge. They would give you information to kind of predict what the possible charges should be. And why do those charges form? Well, they're going to try and get that stable configuration. So remember, we want a full valence shell, or we want a full sublevel, or we want a half-filled sublevel. So all of those charges that you saw on the last slide are a result of trying to become stable configurations. And then one other idea, we talked about this in first year, the word isoelectronic refers to atoms and ions that have identical electron configurations. So for example, you've got neon, magnesium 2+ and F- are all isoelectronic because all of their configurations are 1s2, 2s2, 2p6. Magnesium loses its 2, 3s electrons. Fluorine gains 1 electron to fill up the 2p, and then they both look like neon. So the 3 atoms are isoelectronic to each other. One other idea, we mentioned this once in class, but I wanted to share it with you again. The idea of magnetism has to do with the electron arrangement in the cloud, so I thought this was a good place to put it. When a material is placed within a magnetic field, the magnetic forces of the material's electrons are going to be affected. So you can have electrons that are all paired up. In this case, it's called diamagnetic, and the magnetic field is really going to have no net influence on it. But if you have an odd number of electrons, or you have unpaired electrons more likely, because you can have something where you have 1 electron in 3 orbitals, and each of those could have the same spin, so they're not technically paired. Anything that's paramagnetic is going to be influenced in a magnetic field because you've got electrons spinning one way or another, and so that can influence which direction it's attracted to. Third type of magnetism is ferromagnetic. There's not a whole lot of materials that are ferromagnetic. Elements like iron, nickel, and cobalt and their alloys are typically what we think of as being ferromagnetic. And basically what that means is when you put those atoms in a field, you actually can get all their electrons to line up in the same way. So you're going to give them all the same spin. So it's not a matter of this orbital is an upspin and this orbital is a downspin. You'll have them all directed in the same way, depending upon how you place them in the magnetic field. So that's what ferromagnetic means. When you take the object out of a magnetic field, it actually will stay magnetized. It'll stay with the electron spins in that same direction, which is why you can magnetize a paperclip by bringing it close to a strong magnet, because the iron in the paperclip will keep, the electrons in the iron atoms will keep their spins once they've been influenced by a magnetic field. All right, other properties that we're going to take a look at. Want you to remember, we're going to break this here and I think go to another video to show this. I think we've covered the first half of the material okay. So rest major properties. Remember that these properties you're going to see in the S and the P block, but we're kind of ignoring what happens in the D and the F block because these properties don't come out as much. All right, so on to the next video.